As we begin our study of NMR spectroscopy, it's a good idea to review for a moment or two what the word spectroscopy means. During our education as chemists, we certainly run across the phrase a number of times in general chemistry, organic chemistry, even in classes like instrumental analysis or physical chemistry. We learned that there are many forms of spectroscopy, each of them capable of telling us something different about the atoms and molecules we would like to study. We remember that spectroscopy has something to do with light, and so we're going to look at that one for a moment. Remember, when we say light, we can also say electromagnetic radiation or the electromagnetic spectrum. And remember that this is really a vast phenomenon with many different regions, names like X-rays and gamma rays, ultraviolet light, infrared light, radio waves, microwaves, and then of course visible light, the one part of the electromagnetic spectrum we've been equipped by nature to be able to detect directly. A reminder of a couple of terms when we talk about light. One of them, wavelength, the distance between any two equivalent points on a wave, usually defined crest to crest, and frequency, the number of oscillations in a unit of time, most often defined as simply oscillations or cycles per second, a unit in physics that is known as hertz. The wavelengths range over many orders of magnitude, as seen in this graphic here, from kilometers all the way down to picometers. And I want you to notice as you look at this graphic just how tiny the visible region is in the greater electromagnetic spectrum. It really is amazing how vast the phenomenon we call light is and how small the part of it that we ourselves can directly detect. It doesn't mean we can't build things that detect all the other regions. We do, and those are our spectrometers. Remember that the various areas or various regions of the electromagnetic spectrum tell us different things about our molecules. Infrared spectra, for example, gives us information about molecular vibrations, about how bonds are vibrating. Ultraviolet visible light spectroscopy can give us information about the electrons and the electron energy levels in a molecule or an atom. And then NMR spectroscopy, the focus of our course here, technically tells us about the orientation of the magnetic field of a magnetic nucleus in an external magnetic field. It's a mouthful of words, true, and as we go along in this course, we will explain in great detail exactly what all of that means.
One critical idea common to all forms of spectroscopy, whether it's infrared, UV vis, NMR, or any other form of spectroscopy, is this basic picture. We're going to picture a molecule at a certain level of energy, in an energy state. I'm just going to use this little vertical line to represent our molecule sitting in this energy state. Nearby, available to it, but higher in energy, is a second energy state, unoccupied at the moment. Now what happens is light is going to come along. You'll see that sometimes symbolized h nu to represent a photon. Sometimes you'll see it symbolized by this little wavy arrow to indicate a light wave. But in either case, what happens is our molecule now jumps to the higher energy level. The photon, the light, has given its energy to the atom or molecule and caused it to make this jump to the higher energy state. Now, it's not just any amount of energy. The energy of the photon and the energy difference between these two states have to match perfectly. Too little energy, too much energy, and the light will not cause our molecule or an atom to make this jump in energy. It is this great specificity between the energy of the photon and the transition between these energy states that gives us so much information, especially in NMR spectroscopy. This is an idea and a concept that we will be developing as we move through this class.